questions. Over to you, Tanay.
Uh, yeah, thanks. I think you need to enable sharing or something. Uh,
You can share your screen, right?
yeah, I'm trying.
I think we can see your screen.
Oh,
Yeah,
okay.
we can.
Okay. Did it move shift to the slide?
Yeah.
Okay, thanks.
I mean,
I'll do full screen.
uh, we can see your teams that screen.
Oh, it seems there is some lag then. Uh, okay, now other slide visible?
Yeah, we can see.
Okay, thanks.
Yeah, I can see.
Let me full screen this. Oops. Okay, so let me start. And so thanks for the invite, for giving the talk here about some of our recent work, which is going to come out, I think, early next month in March. So I'm going to be speaking about encoding quantum information into black holes. Uh, this is based on this older paper with Ayan, Alex, and Hariram, and an upcoming paper with Sukrut, Ayan, and Hariram, which will come out, as I said, in March. So here's how I've structured the talk. I'll spend some time on an introduction and some motivation. Then I'll do a bit of a warm-up problem where I'll study a black hole coupled to a classical oscillator. Uh, then I'll quantize the oscillator and study the black hole coupled to the quantum oscillator. Finally, I'll do another example where the black hole is coupled to a qubit, and I'll conclude with some open questions and some future directions. All right, so let me start with an introduction and motivation. So let me start with black hole complementarity. So this was an idea originating to Susskind and others. So what they observed was that information seemed to be both inside and outside of an old black hole. So you seem to be violating the no cloning theorem of quantum mechanics if you assumed the four postulates on the screen. So if you assume that the black hole evaporates via a unitary process and that effective field theory is valid everywhere outside the horizon, and what is now called the fundamental dogma that a faraway observer, when they look at a black hole, they see it as some system, as a usual quantum system with some discrete spectrum. And finally, that there is no drama at the horizon, that an infalling observer doesn't experience anything weird happening as they cross the horizon. So as a consequence of these four postulates, you see that information seems to be both inside and outside an old black hole, and you're violating the no cloning theorem of quantum mechanics. But what these guys proposed, Susskind and others, is that there's no single observer that can actually verify both copies. So although you seem to be cloning quantum information, there's no observer or no experiment you can do to verify that cloning is actually happening. So this is one of the earlier works. Following this, there was this idea of the AMPS or the AMPS-Mathur paradox, which was a violation of the strong subadditivity of von Neumann entropy. So if you consider an old black hole and you split the system into three parts, there's an early radiation part. So it's all the Hawking radiation that's been emitted so far. There's the black hole interior, and then there's the late radiation, that is all the Hawking radiation that will be emitted now or after the page time. So if you split the entire system into these three parts, early radiation, late radiation, and interior, you find a violation of the strong subadditivity of von Neumann entropy. How does that happen? So for a sufficiently old black hole, the Hawking quanta that have already been emitted are maximally entangled with the interior. That just follows from Hawking's original computation. So you have a maximal entanglement between the interior and the early radiation. But if the evaporation process is unitary, you expect that the early radiation will be purified by the late radiation. That is what will give you this famous page curve. So the late radiation and the early radiation are also entangled. So that means that the early radiation is entangled with both the late radiation as well as the interior. But this is an impossibility. In quantum mechanics, entanglement is monogamous. Only two subsystems can be maximally entangled, not more than two. Or you can equivalently say that the strong subadditivity of von Neumann entropy is violated. So assuming these four postulates of complementarity leads you to this conclusion that strong subadditivity is seems to be violated for an old enough black hole. Now there are ways to go around this. There are ways to kind of resolve these issues. One argument was due to Harlow and Hayden, who argued that the complexity of decoding information from the Hawking radiation is exponentially complex. So the evaporation timescale for a black hole is polynomial. It scales like the entropy to the power something. So these guys argued that the amount of time it will take you to decode any information from the radiation will be exponential in the entropy. So by the time you decode anything from the radiation, the black hole will have evaporated away already. So many of these questions that are involved in these paradoxes, such as the AMPS or this previous cloning paradox, these can't be performed even in principle. So to verify that cloning has happened, you have to first decode information from the Hawking radiation, and then jump into the black hole and verify that there is a second copy inside the black hole. But if the decoding process takes a very long time and the black hole doesn't exist anymore, then you can't perform this experiment at all, and you can't verify that there was ever two copies. So this is one way to get around these issues via arguments of complexity. So these answer some of the questions related to this. There have also, so let me come to then uh, why do we need a microstate model? So let me motivate the reasons for thinking about microstate models instead of more circuit models or arguments of these types like the AMPS or Susskind. Yeah. So the reason we need a microstate model or a more dynamical model which goes beyond just quantum circuits is that we need a more precise understanding of how information is encoded into Hawking radiation and the interior, and how it can be decoded. For example, why is it that information is encoded in an exponentially complex manner? And which particular observables do I need to measure in the Hawking radiation to actually be able to decode this? So we asked this question if we can construct a more microscopic model where we don't abandon semi-classical description completely. So we assume that there is no global semi-classical description, but locally you can describe the geometry via semi-classical approximations. And can we explain how this notion of complementarity emerges from a more microstate description? This is the type of questions we have in mind. And for this, in this older work that I mentioned in the beginning, we came up with this particular model. Uh, so what is shown on the screen is a cartoon depiction of the model we look at. So let's say you want to describe the horizon of some higher dimensional black hole. Let's say its horizon is some two-dimensional manifold. So what you do is you take the 2D manifold and you tessellate it by a lattice. And on each vertex of the lattice, I have an ADS2 black hole. And these ADS2 black holes are coupled via some mobile gravitational charges, which take SL2, which have an SL2R symmetry. So these mobile gravitational charges have an SL2R symmetry, and I have these ADS2 black holes at each vertex of this lattice. Now this model is inspired. It's not derived. It's inspired by this picture of fragmentation. So if you take a near extremal black hole and look at its near horizon geometry, it has a ADS2 throat which fragments into multiple ADS2 throats. So that was the kind of inspiration behind constructing this model. So we set up this model and studied dynamics for it and try to understand if it describes real black holes in any sense, or at least some properties of real black holes. So we've managed to identify some solutions of our model of the equations of motion for the model. And these can be interpreted as some microscopic states of the black hole. So it gives you some details on the horizon. We find that the model mimics some relaxation properties of usual black holes after the shock. So if you shock some of these throats, that's equivalent to throwing some compact pieces of matter into the black hole. If you shock some of these throats, the black hole relaxes to a new microstate. So you have an evolution from one static solution to another static solution that can be interpreted as an evolution from a microstate to another microstate. And remarkably, we also find something called classical information mirroring. So there was this idea of quantum information mirroring, which was put out by Hayden and Preskill in 2007. We've only so far studied the classical version of it, and we've seen that this model that I've shown you here actually mimics the classical analog of the Hayden Preskill mirroring. So let me tell you what information mirroring is. Uh, So what these guys did, Hayden and Preskill, is they modeled the evolution of a black hole via a random unitary, which they call U. So you have some black hole which is denoted by B. So B gives you the quantum state of the black hole, and it's some old black hole, so it's maximally entangled with the early radiation, which is denoted by E. So this line joining B and E indicates that there is some number of bell pairs which are shared between B and E. So B and E are maximally entangled. D is some diary which is thrown into the black hole. So Alice wants to destroy some piece of information. So she thinks that, okay, let me throw my diary D into the black hole, and the black hole should scramble it up and it should be lost forever. So she throws some diary D into the black hole. Now this diary is maximally entangled with some reference system S. That's also denoted by this line joining S and D. Now this reference system is purely for reasons of to make the argument simpler. You don't really need it, but this is typically how quantum information literature makes arguments about these ideas. But you don't actually need to consider D to be entangled with anything, but this makes the argument easier. So let me assume that D is entangled with some reference system S. Now the diary is thrown into the black hole, and the black hole dynamics is via some random unitary process, which is denoted by this unitary matrix U. So the unitary acts on D and B, and it scrambles up D into the black hole B. And the output of this unitary process is some new black hole state, which I call B prime, and some new radiation, which is called R. So the process is you throw a diary D into the black hole B. It's scrambled up by this unitary U. You get some new black hole state B prime and some new radiation, which is R. So this is the experiment you perform. So the process is D plus B going to B prime plus R. So the argument that Hayden and Preskill gave was that S and B prime will have zero mutual information. So recall that S and D were maximally entangled. So the fact that S and B prime have zero mutual information implies that the information of the diary is not inside the black hole anymore. So B prime was the new state of the black hole, which contains no information about the diary. So the information about the diary is purely contained in R plus E. So the early plus late radiation will contain the information of the diary completely. So as I said, the information of D is completely in R plus E, where E recall is the early radiation. Now the argument for this was following some of Page's old argument. So the arguments Page used to derive his famous Page curve. These arguments just rely on properties of random unitaries and averages over random unitaries. So what Hayden and Preskill showed more concretely is that if you take the state of SB prime, the joint state of the SB prime Hilbert space, that's denoted by this rho SB prime, you compute the difference of this density matrix with the product density matrix of rho S tensor rho B prime, where this subscript max indicates that rho B prime is the maximally entangled state on the B prime subsystem. So if you compute the norm of this difference between the the density matrix on S B prime and the product density matrix, this norm is upper bounded by the ratio of the sizes of these two subsystems. So this density matrix S B prime is approximately in a product form as long as S is much smaller than R. So as long as sufficient amount of radiation R has already been emitted, then this state is in a product form. That means S and B prime have no mutual information. So as long as sufficient amount of radiation is emitted, S and B prime will have zero mutual information, and all information of this diary is now in R plus E. So this was the process they called information mirroring. Now, why is this mirroring? This is mirroring because the information you throw in comes out very quickly. More precisely, it comes out after the scrambling time of the black hole. So the time it takes for this unitary to scramble up this diary into the black hole. So as soon as you throw something into the black hole, after the scrambling time, it's already revealed into the Hawking radiation. Whereas it takes a much longer time for the interior to be revealed into the radiation. So in that sense, it's like an information mirror. So if you throw something at it, it's reflected back quickly. Right. So in the Hayden-Preskill protocol, Bob, who's sitting here, who has access to R plus E, who's collecting all the radiation, he can decode Alice's diary D without needing any information about the interior. He just needs to have collected the early radiation and the new radiation which emerges. So Bob can decode this mirrored information without needing information about the black hole interior itself. So the question we want to ask is if our toy model can mimic this process. Can we, within this toy model, can we see which observables will encode Alice's diary? Which observables we need to measure to decode information about Alice's diary? So we want to understand precisely how this diary is encoded into this model, which I showed you, and how it can be recovered. So there should be some degrees of freedom in this model, which will encode this mirrored information, and some other degrees of freedom, which will encode the interior. And there should be this split, which will emerge dynamically in this model, which is something we want to study. But this model already was complicated when we studied the classical versions. So quantizing all of the degrees of freedom here is already going to be a big mess. So the first thing we wanted to try was to try a much simpler setup where we'll couple just a single throat, where each of these, you have an ADS2 at each of the vertices, you just take one of them. So you just take a single ADS2 and couple it to some quantum system and study the evolution of that and ask how the initial state of the quantum system is encoded into the black hole. So the problem we'll study on, the problem which I'll focus on for this talk is very simple. I have an ADS2 black hole. I'll couple it at the boundary to some simple quantum system like a few qubits or a quantum harmonic oscillator and study the evolution of the joint system and look at what happens to the initial state of the quantum system and where it's encoded. Right. So that was my rather quick introduction. So are there any questions? Okay. If not, I can move on to some of the results, and let's do a warm-up problem first, where we'll couple the black hole to just a classical oscillator. So let me start with the model for the ADS2 itself. So we have the action for JT gravity, which has a dilaton, which I denote by phi, and some matter action. The second term is the usual Gibbons-Hawking boundary term. Phi b is the boundary value of the dilaton. So notice in the action that a dilaton doesn't couple to the matter directly. So I can just write down equations of motion for the phi, and they'll just be r plus 2 is equal to 0. Sorry, L here is the ADS radius. So if I compute equations of motion for phi, I just get r plus 2 is 0. So the metric will always be locally ADS2. You can compute the equations of motion for the dilaton. They'll look like this. This tells you that bulk matter will reparameterize boundary time. I'll make that precise in a moment. So since the metric is locally ADS2, it's easy to check that the metric I've written here is a solution to the equations of motion, where R is my radial direction, R goes to 0 is the boundary, U is some null coordinate in the bulk, and it's also the physical time at the boundary. Mu here parameterizes the residual gauge freedom here. So I'm fixing my gauge to be the Eddington-Finkelstein gauge, and mu is all the possible residual gauge freedom you have. It's also the ADM mass of the black hole. So this metric corresponds to some black hole, some asymptotically ADS to black hole, and mu is essentially the ADM mass of this black hole. Now you can do a coordinate transformation to transform this metric into pure ADS2. So the metric will then just look like this, where here again rho is the radial coordinate, t is some null vector, t is some null coordinate in the bulk, and the coordinate transformation you need to do is here. So t is now some function of u, and rho is like this. Now what function of u exactly do you need to choose for t of u? That's given by solving this equation. So if you solve this equation for t of u, that will define exactly what this transformation is. Where here SCH denotes the Schwarzian derivative of t with respect to u. So you can transform this metric to the empty ADS metric via this coordinate transformation. And at the boundary, you have a reparameterization of time. So this u goes to some t of u. And within ADS2, this t of u captures all the dynamical freedom that you have. So I can solve for the dynamics completely in terms of this function and its derivatives. In addition to this, I had an S matter piece here. So the S matter we consider is just a free scalar field in the bulk. To choose some particular mass for it, we need to fix a value just because we're doing things numerically. So we fix some value. This field is dual to some operator O, which has the scaling dimension. I can do an asymptotic expansion for this bulk scalar close to the boundary, and it looks like this. So this is the standard near boundary expansion for a bulk scalar field, where J of u here is the boundary source for this scalar. O of u is the wave or the response to the source. So in these setups, we will choose J of u to be either the position of an harmonic oscillator or some other observables, as we'll see later. But for the moment, I fix J of u to be the position of of a simple harmonic oscillator, a classical simple harmonic oscillator. So the setup is I have some black hole in ADS2 given by this metric. I have a scalar field living on this, which is sourced by a boundary source J of u, which is the position of a harmonic oscillator. And I'll evolve this system consistently in time and allow the bulk scalar to back react on the black hole and study the full evolution. So now let me tell you what the equations of motion for the full coupled system are. So the mass evolves in this way. M dot is just the u derivative of the mass. Lambda here is some coupling constant. Delta, as I said, was the scaling dimension of the dual operator. And x is the position of the classical oscillator. So this equation tells you how the mass evolves. And this equation tells you how the oscillator evolves. So without the lambda, this is just the usual oscillator. So I have basically a driven harmonic oscillator where the driving is given by the dual operator O of u. So now you can check with these two equations of motion that we have a total conserved energy, which is defined as follows. So the total energy is just the sum of the mass plus the energy of the oscillator plus an interaction term.
Can I ask a question?
Sure, sure.
The scalar field. I mean, that in the next. I mean, the last slide.
Yeah.
Yeah. So the scalar field on the bulk, and you you will like put this. I mean, this asymptotic expansion is your kind of a boundary condition.
Yes, yeah. So I fixed g of u to be x. That's like the boundary condition for the bulk field.
Okay, I mean, it should go to the harmonic oscillator. I
Position,
mean that.
yes.
Okay. Okay. Thank
Yeah,
you.
so the position of the harmonic oscillator will be the boundary source for this bulk field.
Okay. Okay. Thanks.
Right, thanks for the question. So as I was saying, we get a total conserved energy. This is easy enough to check. You just take a E dot and plug in these equations and you'll see that this is conserved. Where this is an interaction term. This is just the energy of the oscillator without any interaction. And this is just the mass of the black hole. So now we need to do some counting. So the mass scales like order n squared. By n, I mean the usual large n limit n. So m scales as n squared. So that means that the mass it will also need to scale as n squared. This coupling constant scales as n. The dual operator scales as n, and omega has no scaling with the n. By this n, I mean the usual large n that we mean in gauge theory. So let me show you what the evolution looks like. So we need to solve these two equations and the equations for the bulk scalar field. So you'll get the Klein-Gordon equation for the scalar field in the bulk, which we solve numerically. I'm not showing you that equation here. So these two equations along with the Klein-Gordon for the bulk can be solved together numerically, and we obtain the following plots. So firstly, let's look at the purple curve or the magenta curve. That's constant. So that tells me that our numerics are fine. We have a conserved energy during this process. The red curve is the evolution for the mass. So the mass starts off at some value 1. I've plotted half of the mass. So the mass starts off at some value 1. It grows and then finally asymptotically it settles down to some constant value. The blue curve is the energy of the oscillator. So it starts off at some value and it oscillates and decays away to 0. The yellow curve is the interaction energy, which was this term. So it starts off at 0, it gains some value, and then eventually it decays down to 0. So what we find here is not a surprise. What seems to be happening is that the black hole seems to be absorbing all of the energy from the oscillator. So the black hole here seems to be sucking up the energy of the oscillator completely, such that the oscillator just dies down to 0. So this is what you would expect anyway. If you couple a system to a black hole, you would expect the black hole to start absorbing energy from the system. And this is what seems to be happening here. The operator O, or this is actually the expectation value of the dual operator O, it behaves as I've shown here. It oscillates in time and it has a decaying amplitude, which can be fit to an exponential. So it exponentially decays down to 0. On the right hand side in figure B, I've shown the position and the momentum of the harmonic oscillator. So these also have a similar behavior. They are oscillating functions with an exponentially decaying amplitude. So these also eventually decay to 0. So now here itself we can ask how the initial state of this classical oscillator is encoded into this black hole spacetime. So by initial state here, you only have 2 degrees of freedom. You have the initial position and the initial momentum of this classical oscillator. So what we do is we look at the late time ring down of the black hole mass. So if you look at this red curve, at late times, let's say after 10 or after 15, it's almost a constant, but it has oscillations about that constant, and the amplitudes of this oscillations decay to 0. So m qualitatively will also look like this curve, where this value will not be 0, it will be about some other constant value. So m is also like a oscillating function with decaying amplitude. So from such oscillations of the mass, this red curve, I can extract the frequency, the amplitude, and do a Fourier transform to get the phase and so on. So what we find is that the initial position of the oscillator is well correlated with the amplitude of this ring down. So I've started with some 100 random initial conditions for the oscillator, evolved the system numerically and checked what the ring down amplitude is with respect to the initial position. So the amplitude of the ring down seems to encode the initial position. The phase of the ring down seems to encode the initial momenta. There are these outliers. These are largely because we do numerical Fourier transforms, which can cause a lot of noise in the answers for the phase and the amplitude. So modulo these outliers, it seems that the phase is well correlated with pi, and the amplitude is well correlated with xi. So now this was just the classical case. So this was just a classical oscillator coupled to a black hole. The main goal was to study actually a quantum system and couple it to the black hole. So let me come to describing what happens when you couple a black hole to a quantum harmonic oscillator. So here the equations of motion look like this. So if you focus on the first equation, which is the equation for the evolution of the mass, you'll notice that all I've done is replace x here with expectation value of x. What that means is I'm doing a mean field approximation for this evolution. So I'm assuming that the bulk will only see expectation values of this quantum oscillator. So this is the simplest or the most naive way you could couple these two systems together. Uh, so I assume that the black hole or the bulk only sees average values. So it couples to mean values of these observables. So I replace x dot with just expectation x dot. I replace x with just expectation x. So I'm just doing a semi-classical mean field approximation. This is also what you would do if you were doing like GR. If you look at Einstein's equations, you have G mu nu equal to T mu nu. If the bulk matter is quantum, you replace T mu nu with expectation T mu nu. That's the simplest approximation you can do to solve for the system. The second equation here is just the Schrodinger equation for the oscillator. Now, because I'm doing this mean field approximation, and because the black hole is classical and the bulk scalar is also classical, the oscillator evolves via unitary evolution. So it evolves via just the Schrodinger equation. So this is the original Hamiltonian p square plus x squared, and I have this extra interaction term. Here also you can check that we have a total conserved energy, which is again the sum of the mass. Oops, I forgot to put expectation values here. So this is the sum of the mass plus expectation values of x squared and x dot squared here. So these should be expectation values of the squares of these operators. So we have a total conserved energy in these systems as well. Let's study the evolution for such a system, for which we assume that the initial state of the oscillator is of this form. So we assume that the oscillator is initially within just the 0, 1 Fock basis subspace. It's in some arbitrary state within this subspace, and I parameterize the state by these two angles. So it's
Sorry, I
some
couldn't
point on
follow
the
the
block
like.
sphere. Yeah.
What is your like O operator is?
Sorry.
I mean your O is. I mean O operator. What is that?
O is like the dual operator corresponding to this bulk scalar. Or
I
if you want
mean
to,
sitting on the boundary. Okay.
yeah, O is the boundary dual operator of this bulk scalar. Or in this asymptotic expansion is this term.
Okay. Mhm.
Is the normalizable mode of the bulk scalar.
And your fast equation is you are getting from this mass. The equation for mass.
Yeah, this
How you
equation,
get?
yeah, this follows from the equation of motion for the dilaton. So if you solve this equation,
Okay.
that will give you that. Yeah.
Okay. Okay. Thank you.
Solve that equation in this metric, and then you get that answer.
Okay.
Okay, thanks. So as I was saying, we assume that the initial state is within this 0, 1 Fock basis subspace. The Schrodinger equation here is just a driven harmonic oscillator where the driving term is proportional to the position. And this system can actually be solved exactly. There's a well-known prescription to solve harmonic oscillators with such kind of driving. And we can write down actually a closed form solution. The solution is this, where I'll define what psi 0 of t and psi 1 of t are. So psi n of t, it's easy to write them in the position basis. So they look like this. So in this, if you just set xp of t and pp of t to 0, this will just be the usual oscillator energy eigenstates, where HNs are the usual Hermite polynomials, and this is some Gaussian. So if I set xp and pp to 0, this is just the usual oscillator energy eigenstate. So what these science correspond to is just shifted oscillator states. So I have the usual eigenstate of the oscillator, which is centered at x equal to 0. I shift that by some value xp of t. So these are shifted oscillator eigenstates. And this f, which appears as the phase here for this solution, the first term should be familiar. This first term here is just the usual phase term you'll get if you evolve this state by the oscillator Hamiltonian. This is just energy times time, which is the phase you get for the usual evolution of an eigenstate. And this is just the action. I forgot to write the mass here. There's an overall factor of m. So this is just the action for the oscillator, where these functions xp of t and pp of t obey the classical equations of motion. So xp of t solves this classical equation, and pp of t is just xp dot. So you can write down this closed form solution. So if I start with this state, this oscillator evolves into this state and for all times, where I've defined psi 0 of t and psi 1 of t here. So this gives you the solution for the state of the oscillator completely. But we still need to solve these two equations numerically. So these classical equations have to still be solved numerically. So once we solve these, we have the full solution for the oscillator. So now the problem reduces to solving this equation along with this equation and the bulk Klein-Gordon equation for the scalar field. So it's the same as the classical problem we already did. So we can do the numerics and we find interesting results. So what we find is, oh, actually, before I even get to the numerics, let me show you. Let me show you what happens with the numerics first. So as I said before, you have this purple line, which is the total energy. So the total energy is conserved, so our numerics are well behaved. I'm evolving the system correctly. The energy of the oscillator decreases as we saw for the classical case, but it doesn't go completely to 0. It goes down to a value which is of order h bar. In these plots, I've set h bar to 1, but this value is of order h bar. And the mass doesn't absorb all of the energy from the oscillator, but it settles down to some final constant value. The interaction energy, as before, increases initially and then decays down to 0. And the mass has a ring down like pattern as we saw for the classical case as well. So this is what we see generically for initial states within this subspace. So the black hole doesn't absorb all the energy from the oscillator. And this final residual energy in the oscillator is not simply the 0 point energy h bar omega by 2, or it's something more than that. This final value is not simply the 0 point energy. So let's understand a bit more. So as I said, the output state of the oscillator is this, where now xp and pp will obey these equations. Where if you look at these equations, I seem to have set O to be 0. And that is because since this interaction energy is dying out, we find that the response or this dual operator O has a similar behavior where it decays down to 0. So now if you look at very late times where O is very small, the solution to the oscillator is just this, where where I've set O in the right hand side to be 0. So at very late times, the solution for the oscillator is given by these three equations. And this is just the usual equation for a free oscillator. You can write it in terms of these like usual sinusoidal functions. For this particular state, you can compute the expectation value of x. That turns out to be of this form. We find that the expectation value of x at late times vanishes, as we saw before. So if you look at the red curve here, the expectation value of the oscillator will eventually decay to 0. That means this function has to be equal to 0. So using this equation and the form for xp in terms of a and b, a cos plus b sine, I can actually solve for a and b and I get a precise answer. So I have solved for a and b. So I therefore know xp and pp, and I can plug these back into this state, and that gives me the final state of the oscillator, some completely analytic expression for the final state of the oscillator. So maybe that was a bit jumbled up, but the argument is at late times this this operator O vanishes. The expectation value of x also vanishes. So since the O vanishes, I can set the right hand sides to 0 at late times. Then the solution for the oscillator at late times is just given by these equations. I can solve these equations to obtain a solution for xp which looks like this. I can use this to compute expectation value of the x operator, which looks like this. But numerically, we find that this actually is 0. So that enables me to solve for these undetermined constants a and b and determine this trajectory completely. So the moral of the story is that we can determine the final state of the oscillator after this dynamics has died down at the end here. So as we saw here, O was decaying down to 0, expectation X was decaying down to 0, and the interaction energy also seems to decay down to 0. And this will be a generic feature of these kind of models. So what we are consistently finding is when you couple such simple systems to ADS2, the system and the ADS2 seem to be dynamically decoupling at late times. So you'll see that the mass of the black hole is conserved on its own. The energy of the oscillator is also conserved on its own. So at very late times, these two systems are decoupled. So there seems to be a dynamical decoupling of these two systems. And this we find is a generic feature when you couple such simple systems to ADS2. Now let's come to the important question of how you encode the initial state. So we asked the same question, how is data about this initial state? So for example, theta and phi, how can I decode this from the ring down of the mass here? So the mass here again behaves like an oscillating function with a decaying amplitude. So I can extract the phase, the frequency, and the amplitude, and look at which of these observables are correlated with which of the initial state observables. What we find is that the amplitude is correlated with the initial energy. So the amplitude of this black hole ring down encodes the initial energy. You might be worried that these values are rather small, but all of our numerics are done to 100 decimals of precision, and our time steps are much smaller than this order. So these results are numerically pretty robust. Secondly, we find that the phase encodes this ratio of the initial position and the momentum. So if you take the expectation value of x and the expectation of value of p, this ratio is encoded in the phase. And this is nothing, I should have written this in a better way, bro. This is nothing but phi. This x-axis is nothing but this angle phi. So this one of the angles on the Bloch sphere is encoded in the phase, and the initial energy seems to be encoded into the amplitude of the black hole ring down. Now this was just for a pure state. So I always started with this kind of a pure state and showed you what the evolution was like. We can do something similar for a mixed state. The evolution can also be solved similarly. we have a closed form expression for the final density matrix. And here also we find that the initial state can be recovered from the amplitude and the phase, but we need an additional piece of information, which is the decay exponent. So the black hole is an oscillating function with a decaying amplitude, and the amplitude decay can be fit to an exponential, and the exponent is another number we need. So again here the amplitude is well correlated with the initial energy. The phase is well correlated with this ratio for a mixed state, and the decay exponent is well correlated with these components of the density matrix. So the here again we assume that the density matrix is initially in this 0 1 basis, and it has no other component. So this component of the density matrix encodes the decay rate, and you need only these three independent numbers to specify the initial state completely. So the complete initial state is specified in terms of the amplitude, the phase, and the decay exponent. So we find that the complete initial state for a mixed state of the oscillator is encoded into the black hole ring down. This is the main message from this whole study, is that the initial state of this oscillator, if you restrict it to a qubit subspace, it seems to be encoded in this black hole ring down. Now a natural question would be, what happens if instead of a qubit subspace here, I added like a CHEP-2 plus CHEP-3 plus CHEP-4 and so on, as many as you like. The expectation is that within this, at least this leading behavior of the mass, we won't be able to recover the initial state completely. But there could be subleading terms in this evolution of the mass, which we don't see numerically. Maybe we'll see it with higher precision. So those might encode these higher Fock state coefficients. So that was the story for an oscillator, a quantum oscillator coupled to an ADS2 black hole. We can go in a different direction and couple a black hole to a simple qubit or spin half, again at the boundary, and the coupling is via the source as it was before. So we choose the Hamiltonian for the qubit to be just this, where H naught is some magnetic field along the z direction. So you have this usual H naught sigma z Hamiltonian, and then there is some interaction term. So this is like a time dependent transverse field Ising model. So you have the magnetic field along the z direction, and a time dependent magnetic field along the x direction, where the value of this field is given by the dual operator O. And we can parameterize the state of a qubit, the most general state of a qubit, in this way, where U1, U2, U3 are arbitrary real numbers. Sigma x, sigma y, sigma z are just the usual Pauli operators. For this density matrix, you can compute what the purity is, and it looks like this. So purity, I mean, just trace rho squared. It looks like a sum of the u squares plus 1. So now we take this spin and couple it to the bulk scalar field, such that the boundary source for the bulk scalar is of this form. So the bulk scalar couples to expectation value of the sigma x operator, which is appearing in the interaction term. So let me go back and flash this one. So the j here will now be expectation value of sigma x times some lambda. So now I've coupled a single qubit to the bulk scalar field. And similar to before, we can write down equations of motion. I have some equation of motion for m dot, and I have equations of motion for these real numbers which appear in the density matrix u1, u2, and u3. So u1 is just the expectation value of sigma x in this state row. U2 is the expectation value of sigma y in this state row, and so on. So if I know the evolution for u1, u2, u3, I know the evolution for rho completely. Sorry, forgot to say that this I is the identity operator. So now I have evolution equation for the mass and these three numbers which determine the state of the qubit completely. Given these equations, again, it's easy to check that there's a total conserved energy which looks like this. Again, it has the form where it's the sum of the mass plus the energy of the energy of the qubit and an interaction term. Here, h naught needs to be order n squared for there to be a sufficient effect of this coupling on the mass. And it's easy to check from these three equations that u1 squared plus u2 squared plus u3 squared is a constant of motion. So you take these three equations. So here you multiply with a u1, here you multiply with a u2, here you multiply with a u3 and add them up. That will tell you that this is a constant of motion. But this is exactly what appears in the purity. So that tells me that during this evolution, the purity doesn't change. Which should not be a surprise because, as I said before, the evolution is unitary. So the qubit will evolve via the Schrodinger equation with this Hamiltonian. So you would expect that the purity is preserved because it's a unitary evolution. Similarly, the eigenvalues of the density matrix, they're just, there should be a plus or minus here. So these are the two eigenvalues and they are also constants of motion. So the purity and eigenvalues of the density matrix are constants of motion. That tells you all possible Renyi entropies are constants of motion. So let's do the evolution and understand what the energetics are. So here we find again that the mass increases. The mass starts out at some value, it increases and then settles down to some final constant value. We have a total conserved energy, so the numeric should be okay. The energy of the spin starts off at some value and then decays down and then settles to some constant value. The interaction energy has the same behavior as before, it decays to zero. So as I mentioned before, here also we have this dynamical decoupling of these two systems. So we are not setting this lambda to zero by hand. Dynamically, somehow the systems are getting decoupled. The dual operator behaves like this. So here it has some oscillating behavior and again it decays down to zero. The functions u1, u2, u3 have behavior shown in the plot L. So if you focus on u3, what seems to happen is it starts off at some value and then goes to -1. So u3 is the expectation value of sigma z as it appears here, which seems to be going to -1. All of these plots that I'm showing you are for a pure state. So u3 seems to be going to -1, which is the minimal value it can take for a pure state. So what seems to be happening is that u1 and u2 are settling down to 0. Sorry? Sorry, was there a question?
I think no, maybe you
Okay,
can
okay.
go on.
Yeah. So what seems to be happening is that u1 and u2 are settling down to 0 and u3 is taking its minimal value, which in this case was -1 just because the plots I'm showing you is for a pure state. So from that, we've also studied these for mixed states, but I haven't put the plots in the talk. From that, we can conclude that the density matrix of the qubit evolves as follows. So it starts off with this particular form where u1i, u2i, u3i are some initial values, and it evolves to this particular form. So it has no components along sigma x and sigma y, and the component along sigma z is the minimal possible value, which is this, which is just essentially the purity. So the density matrix of this qubit seems to just evolve from this to this. So although you are preserving the purity and the eigenvalues of the density matrix, you seem to be losing information about expectation sigma x and expectation sigma y. You're just left with this single number here. Right. So again, here we can ask the question: what happens to the initial state? How does it get encoded into the ring down? So again, we do the same thing. We look at the late time behavior of this mass, fit it to a oscillating function times a decaying exponent, figure out the amplitude, phase, etc., and check which are correlated with which of these initial values u1i, u2i, u3i. What we find is that the decay exponent, the rate at which the oscillations of the mass decay, that is well correlated with the purity, the purity of the state, and the purity is a constant of motion. So if I this is well correlated with the decay rate. Again, there are a couple of outliers which are due to Fourier transforms and data and fitting these functions to exponentials. That introduces some errors. But we find that the amplitude, phase, and frequency are not well correlated with initial states. So they are not well correlated with these numbers themselves or some nice combinations of these numbers. We can't find a combination that is well correlated with any of these. So it seems that the entire data of the initial state is not encoded into the late time black hole ring down. At least this leading behavior, which we can find numerically. But there is some irreversibility also within the qubit itself. As I mentioned before, you're losing information about the sigma expectation sigma x and expectation sigma y. So the fact that you're losing information on the qubit side seems to also be mirrored on the black hole side, where only partial information of the initial state is preserved in the black hole ring down. So now what was happening here is that you are going from this initial state to a final state which was purely polarized along the sigma z direction. And this sigma z direction was chosen because the Hamiltonian had this term. When lambda goes to 0, the Hamiltonian is along sigma z, which is what decided the direction of this final state. So now a natural question to ask is what happens when I set h naught to 0? So if I set h naught to 0 here, then there's no preferred direction that the spin can go to for this final state. There's no preferred direction which is chosen from the Hamiltonian. So then what happens to the evolution? And we find something remarkable. So here, the interaction energy does not vanish at late times. It starts off at 0, increases, and then settles down to a final constant value. Here again, if you're worried about these values, the same comment applies. Our numerics are pretty precise, so yeah, pretty much confident that this is robust. But something very, very interesting happens to the mass. The mass of the black hole seems to be decreasing from the initial value 1 to some final value. Although we have total conservation of energy. Note that this m is not what is not the ADM mass of the black hole itself. This is the m which appears in the metric. It is the ADM mass will also include this interaction term. So the ADM mass here is constant during the process, but the mass is decay. The m which appears in the metric is decay. So now you might be worried about how this is possible or how this is consistent with the second law of thermodynamics. I'll come to that in a couple of slides. Let me first show you what happens to O and these U1, U2, U3s. So O starts, I've chosen initial condition for O such that it's 0. So it starts off at 0 and then settles down to some final constant value. U1 is a constant. U2 and U3 have some oscillating behavior. Now it's easy to understand why U1 is a constant. If I set H naught to 0 in this Hamiltonian, the H is proportional to sigma x. So if I do a Heisenberg evolution for the operator sigma x, it will be time independent because H comma sigma x is 0. H commutes with sigma x itself. So that explains why U1 is a constant. Sorry, that explains why U1 is a constant, which is the red curve here. Now, since OU settles down to a constant value, let's look at the evolution equations for these guys at late times. They will just look like these. So U1 dot is 0, U2 dot is proportional to U3, and U3 dot is proportional to U2. Where OF here is just the final value for O, where here it will be 0.35 or something. So OF is just the final asymptotic value for O. Now you can take double derivatives. You can take another derivative here and plug in this equation. That will give you the equation for an oscillator. So you'll get U2 double dot is proportional to minus lambda U2. That is what explains this oscillatory behavior. Note this argument is only true at late times. So I'm only describing what happens at late times when O is sufficiently small. Sorry, when O is sufficiently close to its final value. So right, if you were worried about how a decrease in mass is possible if with consistency with the second law, we can compute the entropy, which is just given by this expression, where phi is the dilaton, RH is the event horizon. So we compute the value of the dilaton at the event horizon. This is just the usual RT prescription. So if you do that, you can plot what phi RH is versus time, and it's a monotonically increasing function which settles down to some final value. So this evolution is not in violation of the second law or something like that. So this decrease in mass that we see here is not anything fundamentally weird. So this opens up some nice possibilities. What you could imagine doing is using this black hole to do work on certain systems, to raise the energy of certain systems, to raise the state from a lower energy level to a higher energy level. So you could, in principle, use such a setup to do work on quantum systems using baths that are dual to black holes. So such a setup opens up such possibilities. I'm almost to the end of my talk. Let me just briefly flash something more which can be done within these models. So you can also compute real-time correlation functions within these models. So these are interesting objects for out of equilibrium dynamics. For example, you might be interested to compute 2-point functions, uh, and in this setup with, let's say, a qubit coupled to a black hole, and try to understand what happens to 2-point functions. There's a well-known prescription to do that computation due to Skenderis and others, and this has been extended by more recent work which I've cited here. So we've tried to compute 2-point functions within the setup of a qubit coupled to a classical bulk scalar field. This is work in progress, but what we've managed to find is a notion of an effective temperature for this black hole coupled to a qubit. I've plotted here the inverse temperature versus time. So this interpolates between the initial inverse temperature and the final inverse temperature. So this is
Hi,
just a
Tanay.
hi.
You have 5 more minutes left.
Yeah, I'm almost done. Thanks.
Okay.
Right. So what we have here, we've managed to define a notion of an effective temperature for this setup. Computing 2-point functions is a work in progress. Hopefully that will also be done in a couple of months and put up on the archive. So we can also actually compute correlation functions within these setups. That was the main reason for putting these two slides in. So that was all I wanted to say about the main details of the talk. Let me come to the conclusions and let me describe some open questions and what's planned for the future. So in the beginning, I introduced this microstate model and I motivated all of this talk from ideas of like black hole information and complementarity and so on. I haven't connected these results with that yet. So what we want to do is put all of this together. The microstate model that I showed you, we can add Hawking radiation to it rather easily. So if you followed these recent papers where they've computed the page curve in ADS2, we're using essentially the same setup. So it's very easy to turn on Hawking radiation in these setups. So we can have the microstate model which has this lattice of ADS2 throats. So in this figure, I've drawn a horizon which is just a circle, and I've drawn a simple lattice with just 3 vertices. So I'm describing a lattice version of the horizon in terms of these 3 vertices. Each of these vertices is an ADS2 black hole. On top of this, I can add Hawking radiation and couple each of these throats to some quantum systems. and now ask in this model black hole how the initial state of these qubits are encoded into degrees of freedom of this model. For example, into these hair-like degrees of freedom that I mentioned before, or into parameters of these ADH2 throats, and so on. One could think of coupling entangled qubits to such a model. So, for example, you could couple these two throats, these two ADH2 throats via entangled qubits, and ask questions about the possibilities for constructing like teleportation protocols by using such entangled qubits and the setup that I just described in this talk. So this is work in progress. So the motivation behind doing this simple study of ADS2 plus quantum system was to be able to use these results to study the model that I described in the beginning and actually concretely ask what degrees of freedom in the Hawking radiation or in the model itself will encode information about this kind of matter which is coupled to the black hole. There's some work which is forthcoming and which we are trying to figure out. So in all of this work, if you what we've done is done the semi-classical mean field approximation. So when we went from the classical oscillator to the quantum oscillator, we just replaced the operators with their expectation values in the equations of motion. Now that is a mean field approximation which is only valid in certain limits when the two systems have drastically different time scales and so on. So it's not generically valid. And this mean field approximation was the reason that we were getting unitary evolutions for these quantum systems. Now generically, if you couple a qubit to a bath, like put it in the room you're sitting in, the evolution for the qubit is not unitary. It's via some general quantum channel. So the evolutions we are describing are unitary because of this mean field approximation. So the first goal is to actually quantize the bulk scalar field and study the full quantum channel, the non-unitary quantum channel that will evolve these simple quantum systems. And that will be a relaxation of this mean field approximation, and we'll be able to make more precise statements about the encoding kind of questions that we want to ask. Another direction that we want to look at is to study fermions in the bulk instead of scalar fields. Now there are holographic or semi-holographic models for strange metals which have recently come out. So these kind of studies should have applications towards such models where you try to describe some interesting condensed matter systems using holography. So these might have interesting things to say about such models. And as I mentioned before, we want to couple multiple throats via entangled qubits and study protocols such as quantum teleportation and other interesting protocols one might try to construct using such setups. So the end goal is to put this picture to concretize this picture where we have this microstate model where we have this extra boundary quantum systems which are coupled to this black hole model and study what happens to the initial state of these qubits, how they are entangled into this black hole model. That's the ultimate end goal we want to get. Thanks. That was all I had to say.
Thanks, Tanay. And if there are some questions, so open for the questions. So, I mean, I had one question. Hello.
Yeah.
So, for the quantum harmonic oscillator, so I mean, the energies are going to. You told that it is going to some constant value, not the ground state. So, I mean, is there any significance for that?
Yeah. Let me share again. Right. Let me go back to the oscillator. Right. As you mentioned here, yeah, the energy of the oscillator here is not going to the ground state, or this is not the 0 point energy. So what is happening is, although the system is decoupling, the state of the oscillator is not an energy eigenstate. So it's described by by this quantum trajectory, which is a superposition of these two states.
Okay.
So this is not really an energy eigenstate. But if you can plug this into the Schrodinger equation and it's a solution. So this actually will give you a conserved energy for the oscillator itself. So it's not in some eigenstate, it's some superposition of eigenstates.
Right.
Thanks. Any other question?
So if there's no other question, we can thank the speaker. Okay. Okay. Thanks.
Thanks.